Normally distributed variables. Basic properties of density curves. Property 1. A density curve is always on or above the horizontal axis. Property 2. The total area under a density curve and above the horizontal axis equals 1. Variables and their density curves. For a variable with a density curve, the percentage of all possible observations of the variable that lie within any specified range equals at least approximately the corresponding area under the density curve, expressed as a percentage. Here we have a density curve. We have a point C, and then the area to the left of C is the percentage of all possible observations of the variable that lie to the left of C equals this area, expressed as a percentage. What this means is if we have a continuous random variable, if we find the area to the left of C, which is the percentage of the observations to the left of C, that will be the probability of the observations to the left of C. Another situation would be where we have D, and we have the area to the right of D. The percentage of all possible observations of the variable that lie to the right of D equals this area expressed as a percentage. So again, if our observations are to the right of D, we can find the probability once we have the area. Our third situation will be the percentage of all possible observations of the variable that lie between A and B equals this area expressed as a percentage. And this is the area between A and B. Example. Assume that the variable under consideration has a density curve. The area under the density curve that lies to the right of 14 is 0.362. What percentage of all possible observations of the variable exceed 14? What percentage of all possible observations of the variable are at most 14? First, we want to draw a picture of our normal curve. It goes up from left to right until we reach the middle, the mean, then it goes down from left to right. Since we are given in the problem the area under the curve that lies to the right of 14, the mark on our horizontal line is at 14, so I have a line drawn from my horizontal axis to the curve, and the area to the right of that line is shaded, in this case green, and that area is 0.362. To answer the question, what percentage of all possible observations of the variable exceed 14, I just take my decimal, 3.62, and change it to a percentage. 36.2%. Next, we want the percentage of all possible observations of the variable that are at most 14. So we have our normal curve again. We still have the line at 14. This time we've shaded to the left since the observations are at most 14. We know from the original problem that the area to the right is 0.362. The density curve equals 1. I can find the area to the left by taking 1 minus 0.362, which is 0.638, and change that to a percent. I have 63.8%. Example. Assume that the variable under consideration has a density curve. The area under the density curve that lies between 19 and 25 is 0.645. What percentage of all observations of the variable are either less than 19 or greater than 25? First, we want to draw the density curve, which again goes up from left to right until we get to the mean, then it goes down from left to right and is symmetric. I have two spots on my horizontal axis, 19 and 25. The area to the left of 19 is shaded, and the area to the right of 25 is shaded. That's the percentage we want. We are told in the original problem that the area between 19 and 25 is 0.645. Since the area under the density curve is 1, I can find my area by using 1 minus 0.645, which is 0.355. Changing that to a percent, we have 35.5%. Normally distributed variable. A variable is said to be a normally distributed variable or to have a normal distribution if its distribution has the shape of a normal curve. In the picture of the normal curve, it goes up from left to right, peaks in the middle, then goes down from left to right. Normally distributed variable. If a variable of a population is normally distributed and is the only variable under consideration, common practice is to say that the population is normally distributed, or that it is a normally distributed population. In practice, a distribution is unlikely to have exactly the shape of a normal curve. If a variation's distribution is shaped roughly like a normal curve, we say that the variable has an approximately normally distributed variable, or that it has approximately a normal distribution. Normally distributed variable and normal curve areas. For a normally distributed variable, the percentage of all possible observations that lie within any specified range equals the corresponding area under its associated normal curve expressed as a percentage. This result holds approximately for a variable that is approximately normally distributed. Standard normal distribution, standard normal curve. A normally distributed variable having mean 0 and standard deviation 1 is said to have the standard normal distribution. Its associated normal curve is called the standard normal curve. So the standard normal curve is symmetric, goes up from left to right, has the peak at 0, then goes down from left to right. On my horizontal axis, I have marks at -3, -2, -1, 0, 1, 2, and 3. 0 is our mean, and we have a standard deviation of 1. Most of our data is between the standard deviation of -3 and +3. So the curve is very close to the line when it's to the left of -3 or to the right of +3. Anytime we refer to the standard normal curve, we will refer to this picture. Standardized, normally distributed variable. The standardized version of a normally distributed variable x, z equals x minus the mean divided by the standard deviation, has the standard normal distribution. This formula is helpful in taking our approximate normal distribution and converting it to a standardized normally distributed variable. Standardizing normal distributions. The corresponding mean and standard deviation are the parameters of the normal curve. We have three graphs that are similar to standard normal curves. Our first one has most of its data between -5 and 1. It goes up from left to right until it gets to -2, then it starts to go down from left to right, and it's very similar to our standard normal curve. It has a mean of -2 and a standard deviation of 1. The second graph has most of its data between 1 and 5. It goes up from left to right until it gets to 3, then it goes down from left to right. It is a taller normal curve but it is symmetric about the mean, which is 3, and it has a standard deviation of 1/2. Our third curve is much flatter. Most of the data is between 3 and 15. It goes up from left to right until it gets to 9, then it goes down from left to right. It has a mean of 9 and a standard deviation of 2. Using our z-score formula, z equals x minus the mean divided by the standard deviation, we can convert each of these curves to our standard normal curve. Remember, that curve goes up from left to right until we get to our mean of 0, then it goes down from left to right. The mean is 0, the standard deviation is 1, and most of the data is between -3 and 3. Starting with our green curve, which has the mean of -2 and a standard deviation of 1, we want to use the standardized formula for z for this curve, which is z equals x minus -2 divided by 1. If we pick a random point on the graph, such as -3, I can substitute that for x. Z equals -3 minus -2 divided by 1, which gives us -1/1, or -1. And -1 is the same position on the standard normal curve. For my red graph, we have the mean of 3 and the standard deviation of 1/2. We have the standardized version of z for this curve, which is z equals x minus 3 divided by 1/2. If I pick a point on the horizontal axis for that curve, such as 4, I can substitute that for x. So z would equal 4 minus 3 divided by 1/2, which is 1 divided by 1/2, which results in 2. So the corresponding point on my standard normal curve is 2. For my third graph, the orange one that has the mean of 9 and the standard deviation of 2, I can use the standardized version of z, which is z equals x minus 9 divided by 2. If I pick a point on the horizontal axis for that curve, such as 11, that would be my data point x. So z would equal 11 minus 9 divided by 2, which is 2 divided by 2, or 1. So 1 would be the corresponding point on my standard normal curve. Standard normal curve. Finding percentages for a normally distributed variable from areas under the standard normal curve. You start with your normal curve, which has a mean, mu, and a standard deviation, sigma. Your curve goes up from left to right until it gets to mu, then it goes down from left to right. And we have 2 points on our axis, A and B, which represent 2 data points for our variable x. Our areas are equal. Both the normal curve and the standard normal curve have an area of 1. I can use z equals x minus the mean divided by the standard deviation to convert my normal curve to the standard normal curve. The standard normal curve goes up from left to right until it gets to the mean of 0, then it goes down from left to right. Our horizontal axis is z, and the point on the horizontal axis that would correspond to A would be A minus the mean divided by the standard deviation. Mu would be 0, and B would be B minus the mean divided by the standard deviation. Example. A study finds that the carapace length of an adult spider is normally distributed with a mean of 15.14 millimeters and a standard deviation of 1.47 millimeters. Let x denote carapace length for the adult spider. Sketch the distribution of the variable x. So we start with our normal distribution. The mean is located in the middle of our curve, which is 15.14. Just like with the empirical rule, we are going to add standard deviation going to the right. 15.14 plus 1.47 equals 16.61. 16.61 plus 1.47 equals 18.08. 18.08 plus 1.47 equals 19.55. Going to the left of the mean, we subtract the standard deviation. So 15.14 minus 1.47 is 13.67. 13.67 minus 1.47 is 12.2. 12.2 minus 1.47 is 10.73. Continuing with our example, obtain the standardized version z of x. In order to do that, we have to use our equation z equals x minus the mean divided by the standard deviation. The mean is 15.4 and the standard deviation is 1.47. It becomes z equals x minus 15.14 divided by 1.47. Continuing with our example, identify and sketch the distribution of z. For the distribution of z, our mean will always be 0 and our standard deviation will always be 1. So we get the standard normal curve where we have 0 in the middle, 1, 2, and 3 to the right, -1, -2, and -3 to the left. Continuing with our example, find the z-scores that correspond to the percentage of adult spiders that have a carapace length between 13 millimeters and 14 millimeters. Using the standardized version of x, we first substitute 13. Z equals 13 minus 15.14 divided by 1.47. Going to our calculator, I start with parenthesis 13 minus 15.14, close parenthesis, divide 1.47. Enter. Now I want to round this to 2 decimal places, so my answer is -1.46. Using the standardized version of x, I want to substitute in 14. Z equals 14 minus 15.14 divided by 1.47. Going to my calculator, I want to press second, then enter to get what I just typed in. Using my left arrow, I'm going to highlight the 3 and 13 and change it to a 4, then press enter. Then I want to round to 2 decimal places, and my answer is -0.78. The area is between -1.46 and -0.78. Continuing with our example, find the z-scores that correspond to the percentage of adult spiders that have carapace lengths exceeding 18 millimeters. Starting with our standardized version of x, z equals x minus 15.14 divided by 1.47. I then substitute 18, which is z equals 18 minus 15.14 divided by 1.47. Going to the calculator, I want to press second, then enter to get what I just typed in. I can arrow over and change that 14 to an 18. Enter. And now I have my other answer of 1.95. The area lies to the right of 1.95. Recapping normally distributed variables. Basic property of density curves is that they come close to but never cross the horizontal axis, and the entire area is equal to 1. The standard normal distribution has a mean of 0 and a standard deviation of 1, and the standard normal curve is the normal curve associated with the standard normal distribution. A standardized normally distributed variable uses the formula z equals x minus the mean divided by the standard deviation.